Well, welcome back, everyone. Let me get a moment to get situated here. Well, the exams have now finally been graded, and let's take a look at the summary information here. So the exam 3 solutions are posted at the very end of this long list of review materials. And for this exam, the average came down to 72.6%. Definitely was a tough exam. Maximum grade was 1 point shy of a perfect score, though. So just like the other exams, this is a fraction out of a total amount, 60 points, gets converted to a percent in Moodle. And this part right here is now taking all of your homeworks from homework assignment 1 to a homework assignment 20, all the ones due on the day of that last Friday, as well as exams 1 through 3 to give you your most accurate course score. But that course score has the potential to change quite a lot since, let's go to the syllabus next. At the moment, exams 1 through 3 are being weighted as a full-on 70%. So once we go to take the final exam, that changes quite a lot. Exams 1 through 3 get de-emphasized down to 45% from 70, and the final exam in this class is worth 25%. So really the major things that are going to impact the grade the most at the end is your homework score. I'll accept those even late for full credit, and the final exam score. So that's where we're at so far. Any questions folks would like to go over on the last exam? Let me scroll back down while we think about that. Some of the website gets really long after a while. Okay, feel free to interject if there's anything on the exam you folks would like to take another look at, but let's keep on going with the announcements. Aside from the fact that we're about to finish off section 11.10, and we'll come back on Wednesday in chapter 10, finishing off the last bits of the course material. Next week we'll be totally off. I'll still take questions by email as usual, so don't hesitate to send questions. And then on this week, we're coming back to 1 normal day, finishing off content, and then 2 review days on Wednesday and Thursday for the upcoming final exam. Final exam has been posted, information's been posted here. It's Monday, December 9th at the worst time ever, but I'll be here 8 p.m. to 10 p.m. If this is a rough time for you, it often is for people who take this class at that time. I am giving another exam at 5:30 p.m., same exact classroom. Just email me to let me know you'd like to join it at the 5:30 to 7:30 slot, and that will work out just fine. Those classes aren't too big, so everyone could fit. And aside from that, there's also the extra credit opportunities that I posted here recently as well. The first one is relative to the course evaluation for the Moodle, for the course itself. It can be found in Moodle by opening up the block drawer, and then it's the first link right here. This is actually buried at the very bottom. I just moved it up to the top, so it might be harder to find in other Moodle classes. But I also posted it right over here. So if you prefer, you can just click off this. It takes you to the course evaluation for this class. It also gives you a pretty good preamble of why we do it. The short of the answer is because the State Board of Education of Idaho requires it, so we must. They are the one that pays the bills. They're my boss's bosses. The way the course evaluation extra credit works is click here to start answering the questions. It takes about 10 to 15 minutes is what we're told to tell students, but it's really up to you how much information you want to put on there, how long it takes. When you get to the very end on that, there's a completion page that just simply says, "Thank you for doing the evaluation." If you take a screenshot of that completion page, send it to this email, then I'll record the extra credit. And what I'll do is drop an additional lowest homework grade at the end of the semester for a total of 3 instead of 2. So that's how the extra credit opportunity works. Any questions about it, folks? Okay. And the third extra credit, or the second extra credit opportunity down here, I think this was hinted at very early on in the semester. Someone asked about it, but just to make it official, here it is once again. The idea behind this is one bad exam really shouldn't drop your letter grade in your class. So if your final exam is high enough to replace the minimum grade amongst exams 1, 2, and 3, it will full on replace that grade. And just for the sake of a really fast example, let's put down some numbers. I find this makes more sense if you just put down numbers to explain it. Let's assume someone's final exam grade came out to 82%. That's respectively high in this class. And maybe their exams were something like 90. Exam 2 may be 76. Exam 3 may be 94. If this was someone's situation, then what would happen is I would take this, delete that, and overwrite it with 82%. So it can bring up your minimum exam score. If this instead was something like 100%, that would mean nothing here changes. So in other words, it can't hurt your score. Or let me say it a better way. If this was like 70%, so that all 3 of these exams are higher, then you just keep your original exam grades. It won't drop anything. So that's that extra credit opportunity there. Extra credit opportunity there. Any questions at all, folks, with those announcements?
So if I get an 82 on my final exam, I get 82% of 25% towards my final grade?
That's correct, yes.
Okay.
Any other questions so far? Okay. Other thing that I usually don't mention right here, but I was just thinking about it, is when I say the final exam grade will replace your minimum grade, the final exam is the one grade that I sometimes do curve in this course. I never curved my original exam grades unless something crazy went on that just warranted it. But when I go to calculate the final exam grades, my goal when I write the final exam is to write a final exam that doesn't really change the average grade in the entire class. So if I notice maybe the average grade in the entire class is maybe 76%, but after the final it dropped down to 71%, that's a pretty huge drop. I would probably curve the final exam to bring it back up to the 76%. So the final exam wasn't that pivotal. It really shouldn't be. So when I go to apply this extra credit opportunity, the final exam grade that gets put in is the curved final exam grade. So whatever the curved grade comes out as, it replaces the minimum score up here. Well, I think that's my full spiel for the announcements. Any last questions, comments, or anything else? Okay, when we get closer to this entire holiday right here, that's when I'm gonna, the weekend before this, start posting information down here for review information. Could be things like sample exams and that kind of stuff, just to assist with getting through the final exam. So I'll be posting those soon for folks that would like to get studying earlier. But I would say probably the best thing you could do right now is put your old exam 1, 2, and 3 together. If you can resolve those problems cold, you're doing really great for the final exam. We still need some good review problems for this kind of content though. So this is where we left off, section 11.10. We didn't do too much on these notes, but we're now on example 3, where we're going to come up with Maclaurin series for these kinds of functions here. So the way this problem goes is, notice the instruction says, use a Maclaurin series to obtain the Maclaurin series for the given function. So we're not using the actual definition of a Maclaurin series. It means we're using this table up above. So let's take a gander of this table. It has just about everything you would want. The geometric series we used in section 11.8, let me think about that. I think that was 11.9 rather, when we were representing functions as power series for the first time. E to the x we derived recently, and sine x, cosine x are also on the list here. One thing that's kind of interesting about these functions that's really worth pointing out, not that we're at this stage of the mathematical development, is that sine function and cosine functions are pretty bizarre in a certain sense. If you look at the sine function, this is an odd function in the sense that it's symmetric about the origin. You can flip the graph about the y-axis and then again about the x-axis, and every single point matches up. Excuse me. Yes, the points all would match up on this graph if we reflect twice. So we have symmetry about the origin. And that means sine x, we call it an odd function when it has that kind of symmetry. And looking at the powers That makes sense. Every one of these powers is odd. 2n plus 1 is always an odd integer. Likewise, if you look at cosine, it involves powers 2n. 2 to the n is always even. And as a graph, cosine is also an even function because this function is symmetric just about the y-axis. So it's a kind of a neat tie-in that cosine is an even function, and it should be because the powers on its expansion are even. And likewise for sine. That's some way people try to memorize these things. And what else do we have on this list? Well, not too much more. The good news about either the x sine x and cosine x is their radiuses are infinity. I think that's radii. But anyways, the geometric series is limited with a radius of 1. So is tangent inverse. Natural logarithm, same issue. And binomial series, the same issue. But these are still pretty interesting series to work with. And what we're going to be doing next is coming up with more Maclaurin series based off that table above. So here's how it goes. When it says use a Maclaurin series, it means really just do a table lookup. The thing we're going to look up is the one for cosine, because cosine appears in this problem. So we have from a table lookup, the table right above, cosine at x is a summation from 0 to infinity. It's alternating, and then we have x to an odd power, and a 2n plus 1 factorial, same power down below, and the radius is infinity. You have to state our radius of convergence at the end of this problem, but it's not a ratio test. We're just going to inherit the radiance from the original Maclaurin series. So at this stage, well, the problem becomes very similar to what we did in section 11.9 when we were just using the geometric series. We can write that f of x equals x squared. For this part, cosine 3x. What we're doing is taking an x variable here and overwriting whatever x is into that position right there. Won't change the radius, still will be infinity. So we'll go summation from 0 to infinity, -1 to the nth power, 3x to the power of n, or excuse me, not quite to the power of n. Let me try again on that. We were just saying it's an even function, so it should be 2n. That's a little bit more accurate. Divide by 2n factorial. We should do a little bit more work on this to consolidate our bases. X squared can combine with this up here. So this is a summation from 0 to infinity. -1 power n. 2 power of n gets attached to the power 3, and this becomes 9 to the power of n if you decide to use 2 to square your 3. 3 to the power 2n is just as good if you prefer. Then x to the power 2n plus 2. The plus 2 came from that x squared up in front. So we multiplied it up here and increased the power. Denominator is still 2n factorial. Let me change the color coding on that part. So that's the entire process. We just use the known Maclaurin series to rewrite this new expression involving cosine. It has the same radius, so we just state radius is infinity, and we're done with that problem. Any questions at all, folks, getting the result here? Okay, it seems like a parlor trick. We might wonder, what good does this do us? X squared cosine 3x is a perfectly fine function. And so is this one. The radius is infinity as well. But if this was a difficult integral problem, we might be able to find an easier answer than trying to come from an antiderivative. Yeah, go ahead.
Why doesn't it say that cosine x is equal to x 2n plus 1 and then over 2n plus 1 factorial?
Oh, geez, that must have been a mistake. Sorry about that. Looking at the table lookup, I should have been grabbing that, x to the 2n factorial. I think I got the right thing over here. Over here, it should have been 2n like that. Let me put this in red just to show that change. Should have been just a 2n factorial. and then a 2n right here. So 2 changes. Thanks for spotting that, Bryson. Does that make sense with the correction? Okay, so pretty much all we did was take 3x right here, plopped it right inside this location with the correct version of the one for cosine, and that's how the power series proceeds from that step on. Well, let's try it again. We have a new function, g of x is e to the power 2x. Step 1 is a table lookup. Let me try to do this a little bit more carefully. Well, e to the x is not too bad as far as power series go. That's one we derived as well. From a table lookup, we have that e to the x, now as a power series, is an infinite sum, indexed from 0 to infinity, of x to the nth power divided by n factorial. So we took a perfectly good exponential function, and as a power series, well, that's just as good. It has radius infinity, but it only has the side effect that it takes infinitely many terms to evaluate it exactly. But because the denominator is a factorial, not too many terms are really needed to get high accuracy, because these terms converge to 0 extremely rapidly, because the factorial becomes large extremely rapidly. So now that's our power series. We're going to use the same exact strategy of taking this x, plugging that in. And this one's ready to go. There's no extra steps we need to worry about. We're just going to take the 2x, plug it in right there. So g of x is a summation from 0 up to infinity of the nth power of 2x divided by n factorial. And if you took an extra step, the extra step would look like this. Infinite sum from 0 to infinity to the power of n times x power of n divided by n factorial. The fact that we took a x and replaced a 2x in this location doesn't change the radius of convergence. So we say r equals infinity like before, like the original Maclaurin series rather. We did it, folks. Those are 2 really fast Maclaurin series, but that's because we were just using known values for the Maclaurin series for those functions. Any questions at all getting through these? Okay, and we mentioned before that if you left your answer like this, it is really okay. The reason we always took those additional steps is if we had to do something extra, maybe differentiate the power series or integrate it. A big goal for us was to use power series to actually integrate these kind of problems. This is the example that our author pointed out as having no elementary antiderivative. But there's in fact a lot of functions like that. One thing to think about when it comes to integration is that integration is extremely weird and difficult in a certain sense. Here's an analogy. Integration is analogous to prime factorization. So in other words, differentiation is like multiplication. It doesn't matter what function you give me. If it's a differentiable function, our differentiation formulas are going to tell us the process of finding the derivative every single time. And so is multiplication of ordinary numbers. Any 2 numbers you give us, we can multiply them and get an answer. Reversing it is hard though. So integration is like prime factorization in the sense that it is exceedingly hard to factor. Let's call this 2 to the power of 1,000. I guess that's 10,000. Let's go with it. Minus 1. That's what makes it really hard now. This is an odd number, and by factoring that to prime factors is amazingly difficult. It takes a lot of computation power. This is what public security is based on for whenever you're doing online banking. Factoring prime numbers is difficult, so they use that as a public key. Integration is just like that. If you're grabbing just a random function that no one took a look at and say, try to integrate it, the chances are it's not integrable in the sense that we can find a closed form answer. We might have to use power series to actually evaluate this. And these are well, this one's not too random. This one's been hinted at. But this one's pretty random. Finding the antiderivative of this, I'm not too sure if it could be done. But as a power series, the answer is pretty rapid. So in example 4, we'll evaluate the indefinite integral as an infinite series and state the radius of convergence. So we'll give it a try on this one to start. First thing we do is another table lookup. E to the power of x, like before, is summation from 0 to infinity. X power of n, divide by n factorial. Radius for this thing is infinity. So when we go down here to integrate this problem, there's a couple approaches. You could use the fundamental theorem of calculus part 1. We showed how that went. It has its own side effect. If you're going to use fundamental theorem of calculus part 1, now you need trapezoid rule or Simpson's rule and so on to evaluate your result there. So this is a different type of result where we're going to take and integrate this result. Take that x squared you see here, plug it inside this power series. So now it's summation from 0 to infinity of x squared to power of n, which is then divided by n factorial. We need to say dx to make it a proper statement of integration. So this is what we'll be integrating right here. Let's do a little bit of work on that first. This is the antiderivative of infinitely many terms, so 0 to infinity. Multiplying out power 2 to power of n gives us x to the power 2n over n factorial dx. Now, when we go to integrate, because we say dx right here, we're integrating with respect to x. And the only thing that involves x is x power 2n. Everything else is constant. So the end result is we get a constant of integration to start because it is a general antiderivative. Add a new summation, still indexed from 0 to infinity. Antiderivative here will give us x to the power 2n plus 1. And then that means down below we have 2n plus 1 times n factorial. Radius of convergence, you'll never need to use the ratio test for this. We'll just say it's the same as the old radius of convergence, infinity. So this is a fantastically hard problem to get an antiderivative out. But if you're okay with the infinite sum, this is a sum that converges extremely fast, another factorial in the denominator. So you can determine great accuracy with finitely many terms, not too many of them. But as the terms go off to infinity, it becomes the exact antiderivative. When our author says there's no closed form solution to either the x squared antiderivative, what he's really saying is that function there is a power series doesn't have a closed form way of answering it without involving infinitely many terms. It's the only way to write down this function. That's a pretty bizarre view of functions once again. But any last questions, folks, on our evaluation there for part A? Okay, so now we can integrate some pretty wild stuff. Sorry, I locked my keyboard tray. Let's try it again for part B. It's sine x divided by x dx. Well, first thing we need is a table lookup, right? Let's be careful with that. I think I messed that up once already today. For sine x, that's the one that I think I put in erroneously up above that we had to fix. So this will be our power series for sine x in the numerator. Let's write out sine x, sum from 0 to infinity, -1 to n. It's an odd function, so here's where 2n plus 1 really goes. Divide by 2n plus 1 factorial, with the radiuses of infinity like before. This gets a little bit trickier though, because we're dividing by x, we're taking down that exponent by 1. Let's carefully show that step on this one. So antiderivative of 1 over x The power series for sine x goes like this. 0 to infinity in summation. -1 to the nth power. X 2n plus 1. 2n plus 1 factorial dx. So we've got it, folks. This is what we're integrating. But this 1 over x combines with the base x here, drops the power down by 1. So now this is summation. N from 0 to infinity being integrated. -1 to the x power. X to the power 2n. 2n plus 1 factorial dx. Does that look right to folks with that step put in there? Okay, just a little bit yellow highlighting to show for integrating with respect to x, all this stuff, the alternating part, -1 to a power, the 2n plus 1 factorial part, this is all regarded as constant. All that's going to happen is power goes up again. Now it's back to 2n plus 1, and we divide by that new power. I omitted an equality sign. That always looks a little bit weird. Let's put that in so it's not so jarring. So this whole thing is now equal to arbitrary constant of integration plus a summation from 0 to infinity, almost the same as before, but with the alteration. X is now to the power 2n plus 1, since we integrated. Denominator is now that power 2n plus 1, multiplied by the factorial that was already there, 2n plus 1 factorial. And we have that huge theorem in section 11.9 that says, if the original series had radius of infinity, and we did some manipulations integrating, for example, or dividing by x, it didn't affect the radius of convergence whatsoever, still infinity. I keep harping on this part because what you don't want to do in these problems is use the ratio test again. You get infinity, but it's work that you probably better focus on learning other topics. Ratio test, when you don't have to apply it, it's best to skip through it. Well, we did it, folks. Those were some of the weirdest integration problems ever. Any questions so far? Okay. Well, let's take a look at some of the other problems we have down below. When we get to this side of the notes, to me, these are the applications of Taylor and Maclaurin series. There's even more applications. There's section 11.10. We're not going to make it to that section for time consideration. But if you're interested in even more applications or direct applications to physics and engineering, section 11.11 has some great examples. But here's some applications that are already pretty immediate to our course content. We hinted at this one, solving a differential equation like this one. This is a degree 1 linear differential equation. That one's actually pretty difficult. So we're going to solve this thing and express our answer using a power series. Not because it's a clever trick, but it's more we just have to. And what this implies is it's a pretty simplistic looking differential equation. The ones you get in the sciences could look like this or more bizarre. It kind of hints at power series are things that you just have to deal with whenever you're looking into differential equations. They will come up. So here's how we're going to start off this one, though. Let me just rewrite the problem. Y prime plus 2xy equals 1. This is not in a good format to skip the integrating factor, so we begin by looking at this part of the function. This is p of x. The integrating factor, which is labeled as I of x, is e to the power of the antiderivative of p of x. So that's what our integrating factor is going to come out as. It means we're taking e to the power of the antiderivative 2x. Antiderivative of 2x is e to the power x squared altogether. So now we're back to this wonky function. Let me see if I can write it in a way that doesn't look too hard to look at. So we're back to e power x squared. We take e power of x squared and just multiply it to all three sides of the original differential equation. So on this line, we now have e to the x squared, y prime, plus 2x e to the x squared y equals e to the x squared. On the left-hand side, we have the result of a product rule, so we can take all of this stuff and rewrite e to the x squared y prime equals e to the x squared. And double checking this, if you differentiate e to the x squared, you'll get e to the x squared times 2x through the chain rule. That's a check that this really is going out in the way we intended. Next thing we do is integrate both sides as it stands. And that's what the integration would look like on the right-hand side. Because we've already done that integral as a power series, let's double check our answer. There is no reason to reinvent the wheel. We'll take this as our expression. Let's just put it here just for the moment and say, when you integrate the left-hand side, you get e to the x squared y. Integrating the right-hand side gives us this whole result, constant plus a summation from 0 to infinity, x to the power 2n plus 1, 2n plus 1 times n factorial, with the radius of convergence being infinite. So let's just double check we've got it in. Okay, I think we've got it. So we've integrated on the right-hand side, in not the world's most satisfying way, but that's a nice function that does converge rapidly. Finally, we can solve for y by saying y equals either divide everything by e to the x squared or multiply by everything to the e to the power of negative x squared, really up to how you like to format the answer. Going this way, you'll have to multiply the constant plus summation from 0 to infinity, x power 2n plus 1, 2n plus 1, n factorial. Radius still infinity. So this is a pretty decent differential equation. Doesn't look like it would have gone crazy, but out of nowhere, you have to integrate this function, no closed form answer whatsoever. This is about the best answer we can give for this differential equation without using the fundamental theorem of calculus and having to use trapezoid rule and that other kind of method. But notice, even if you did use the fundamental theorem of calculus part 1 and decided, yes, we're just going to use Simpson's rule or the trapezoid rule, it's still a sum you're using. You're still using finite many terms in that sum. This is just a different, more accurate competing approach, I'd say, for the time invested. But that's one application. We can now solve a much wider class of differential equations. And a lot of the really honest ones that tie in together with real-world examples have this feature, unfortunately, where you do need power series to express the answer. Any questions at all, folks, before we try another application? Okay, we've got a couple more left over for the day. We have this one here that we were taking a look at. And from a suggestion from class, example 7 was invented out of thin air. We'll take a look at this one as well. These problems are a little bit longer, so let's see if we can put them on a new page. Example 6 is a really special problem in a certain sense because it's important to remember how weird sine and cosine really are. How do you define them? You start with x squared plus y squared equals 1. It's the equation of a unit circle. There is the unit circle. Then you pick a radian measurement. Let's say this is our radian measurement, theta. It terminates in a point. This just keeps getting weirder and weirder when you really think about these trig functions. When it terminates in a point, you have coordinates x comma y, and then you say the following. Define cosine at theta is x, sine at theta is y. And that's a pretty bizarre way to define any set of functions through a geometric object with an angle measurement at the top of it. Questions people have when they see this is, okay, but what's the real definition of cosine? It's that's your cosine right here. And importantly, this is what the expansion would look like for finitely many terms. So that's how you define the functions. It gets even weirder. If you combine this with a complex number and the base e exponential, you now have a representation of cosine and sine altogether in this way. So we're going to show just how that goes together, starting with maybe the complex number I. The more and more calculus you take, the less easy it is to ignore complex numbers like this. So start off with I, the square root -1. That would mean I squared is -1. I cubed is -I. And I to the power 4 would be +1. The way that goes is, if you want to show what I cubed is, for example, you just take your I squared, multiply it by I. If you want to show I power 4 is 1, you could just take I squared times I squared. That takes you to I power 4. But it's just -1 times -1, giving you a +1. Then this chart just repeats forever, but let's write down 4 more just for the sake of making it concrete. I to the power 5 would be I to the power of 6 is now -1 because you're taking I times I on this prior entry, giving us I squared for -1. And notice the values are definitely just repeating. To get I power 7, multiply prior result by I, it's now -I. I power of 8, it's multiplying prior result by I, but that would be -1 times I squared, which is another -1, so it's +1, and so on. This chart just keeps on going forever. So what else we have? We've got that cosine x is a summation that goes like this: -1 to the nth power, x to an even power, divided by 2n factorial. But for this derivation, we're more interested in the expanded form to see how it all goes together. So if you plug 0 inside here, you have -1 to the power of 0, x to the power of 0, that's all a 1. 0 factorial is just a 1. That's why the first term is 1. Then it goes by evens, minus x squared over 2 factorial, alternating, x4 over 4 factorial, and so on. Let's write in a few of those. 1 minus x squared over 2 plus x power 4 over 4 factorial. And I think I already messed up. Let me try again. It's alternating, so positive to negative to positive to negative. X power 6, 6 factorial, plus x power 8 over 8 factorial. And that should be enough terms for cosine. Last is sine x. And for sine x, what's all the terms that we're missing here, essentially, right? So if we go and take another look at that, sine x involves x, then the value that's odd, x cubed over 3 factorial, the next odd, x5 over 5 factorial, and so on. So it's kind of like all the missing values here when we were alternating from all the even ones. We're grabbing all the odd ones now, so it's going to go x. Let me try a little harder on that x. Okay, it's going to go x minus x cubed over 3 factorial. It's alternating, so now plus x power 5 over 5 factorial minus x power 7 over 7 factorial plus x power 9 over 9 factorial. So we've got cosine and sine all set up. We need one more. E to the x is a summation from 0 to infinity of x power of n over n factorial. But if you expand this one out, it goes 1 plus x squared over 2 plus x cubed over 3 factorial plus x power 4 over 4 factorial, and so on that one. So this one takes all of the terms. It's not skipping anything whatsoever. And finally, we can come back to this. What we really want to take is e to the power of ix. That means we're plugging ix for x there, as well as over there. It goes into all these positions where x occurs. That means I is being raised to a power as well, but we're going to grab the right-hand sides from this chart to simplify as we go. So let's give this a try. E to the power of I times x. We're plugging I times x in everywhere x occurs, so let's just first write this out. 1 plus, on this location, it'll be I squared. Actually, let's write that out just so that we can see how it's all really coming together. It'll be I squared over x squared over 2 plus, next is I cubed over x cubed over 3 factorial. I said that weird. I cubed times x cubed over 3 factorial. And so on down the line. I power 4, x power 4 over 4 factorial. It's going to be slightly painful. To really see the pattern, I need to go up to x power 9. So let's just write these in. I power 5, x to the 5th power, 5 factorial. I power 6, x to the 6th power, 6 factorial. I to the 7th power, x to the 7th power, 7 factorial. Almost there. I to the 8th power, x to the 8th power, 8 factorial. I to power 9 times x power 9 over 9 factorial. And it just keeps on going in that way. But now we can use all this information to start simplifying these things down. So let me double check what I put here though. The expansion of e to the x, I think I missed a term on that. It's 1 plus x squared over 2. Should have really went like that. Sorry, I forgot that one term there. That's enough to throw the whole thing off. Let me see if I can insert that one term here. So a little bit of typesetting magic. E power ix is going to be equal to 1. That's this term. This is the term I omitted, plus ix. Okay, I think we got it. So now we're going to plug in all of these values that we see in green. The one that's I, we'll just leave as I in that position there. And we can say that this is equal to now we've got, let's see here, different powers of I. And starting with these ones, I want to grab the ones where, let's see here. I think I'm getting a little bit mixed up on the steps. Let me take an additional step and start, instead of trying to skip through so much. Let's go 1 plus ix. And then on this one, which is I squared, we can put in the -1. So this will be minus x squared over 2. I'll put in green whenever we change something from I squared. So this will be minus x squared over 2 like that. So all I've done is change the I squared. On this one for I cubed, we get minus I x cubed over 3 factorial. This one, I power 4, gives us just a positive 1. So we'll go plus x power 4 over 4 factorial. I power 5 is just I, so this is plus I. X power 5 over 5 factorial. Plus, now we're up to x power 6, so that's really a minus. X power 6 is -1, so it's negative x power 6 over 6 factorial. Now, x power 7 is negative I. X power 7, 7 factorial. We're getting through it. I power 8 is just a 1. So this term is plus x power 8, 8 factorial. Now, if I power of 8 is a 1, I to the power of 9 is I. So this will be plus I. X power 9 over 9 factorial. and plus and so on. Pattern just keeps on going down the line. So now that we got this far, here's the next key step. Notice that I survives. It's in several places. Let me highlight this one a little bit better. Half our terms involve the complex unit I, square root negative 1. The other half of our terms do not. So that means we can separate some of these terms together. We'll start with the terms that do not involve the complex unit. It starts right here for the 1. So we now have that this is equal to 1 minus, skip over to here, x squared over 2. Skip over to here, plus x power 4 over 4 factorial. Skip all the way to this one, minus x power 6 over 6 factorial. Then we skip over to this one, plus x power 8, 8 factorial. It keeps on going, so we'll use the dot, dot, dot shorthand to signify that. Now, everything else involves I. That means I can be factored out and written this way. I times the result of. Now we're plugging in everything that had a factor of I, but we're only writing the factor without I. So we'll take out x, I is already factored out. Skip to this one, this is going to be minus x cubed over 3 factorial. Skip all the way to this one, plus x power 5 over 5 factorial, way over to this one, minus x power 6, 6 factorial, last one, plus x power 8 over 8 factorial, and then here's our dot, dot, dot to say, and that goes on forever. But now take a look at what we have. Cosine x goes in this way. It alternates, the powers and the factorials are always even. 1 minus x squared over 2 plus x squared power 4 over 4 factorial. That's just all this stuff. So this right here is cosine x as a power series. Sine goes odds, starting with x, then minus x cubed over 3 factorial. That's what we have here. Then it has to alternate to the next odd, x power 5 over 5 factorial. And then that looks like a mistake. Let's take a look at what happened there. I grabbed this one, but I need to grab the one involving I. Let's correct the record on that. That is definitely not going to work for us. That's not only incorrect, but it would throw off the whole result. That wouldn't have been sine. That should have been an x power 7 over 7 factorial. Okay, so lots of stuff to pick out there. Then it should have been up to this one, x power 9 over 9 factorial. So I needed to grab that one and that one. Looks like I grabbed the evens out of nowhere. I was doing so far so good until I got to that last two. But double checking this once again, sine goes by odds, and we are going by odds as well. So this is now, after the correction, certainly the power series, the Maclaurin series in particular, for sine x. All of this started at e to the power by x, using a known power series with radius of convergence, r is infinity. So what we're about to write also has the same radius of convergence infinity as well, and we get to this conclusion. E to the power of ix is now equal to, through the power series expansion, cosine x from this part, plus I times sine x from the second part. And that's the result that we want to show. So I hope this, in some sense, makes these power series feel a little bit more concrete. But you know, the real goal with doing this kind of problem is to highlight trig functions are really bizarre objects. They're defined through an algebraic structure like this. Writing them down as power series gives us interesting alternating series tied together with the exponential function. And so now e to the x cosine x and sine x are all tied together with the complex unit I, square root -1. And you can now do really bizarre things with this. For example, this is the end of our result, but you could calculate e to the power of I times pi using the formula above. It would be equal to cosine pi plus I times sine pi. Cosine pi is -1, sine pi of 0. So now we have an evaluation of an exponential function using a complex value I times an irrational number pi equaling -1. This is a pretty bizarre equation. And sometimes people format this equation even differently. It's up to your stylistic choice. You could write now e to the power of I times pi plus 1 is 0. Really up to you, but that's the number e, which is approximately 2.71. Euler's number. Is now tying together square root of -1, pi, and constants like 1 and 0. So that's a pretty fantastically crazy equation in the sense that these are things you wouldn't necessarily associate together. But because trigonometry is weird enough, this is an equation that gets used a lot in complex analysis. In trigonometry as well, this gets used. And so it's just another way to view those original functions, sine and cosine now. We have other functions we want to take a look at, the hyperbolics. But any questions or comments, folks, with this derivation? Okay, it's a long derivation. Took me some corrections to get through it. But there's a reward to this kind of stuff. If you're interested in these kinds of things, questions like what we see here sometimes make their way to the final exam as a bonus question for extra credit. It's nothing major. It's at the very end of the exam, and you're encouraged to ignore it unless you actually have extra time and you've solved all the original problems. But these last derivations we're seeing on the notes, examples 6. Yeah, starting with example 6. These are things that if you are interested in this kind of stuff, you could try this out again on the final exam to see how it goes. And let's try out this one next, example 7. So e to the x is also mixed together with the hyperbolics, hyperbolic cosine, hyperbolic sine. And the hyperbolic functions are defined in a pretty bizarre way. They're defined by using x squared minus y squared equals 1. So this gives us a hyperbola from which cosh and sinh are defined. So we have a hyperbola and used to define sine hx, cosine hx. But although that's how the hyperbolic functions are defined, with a lot of work and creativity, they eventually get defined this way. We can show that cosh x, this is sometimes taken as the definition of the hyperbolics. It's e to the x plus e power -x divided by 2. But really the way the hyperbolics are actually defined is just like trigonometry with one change, a minus right there instead of a plus, giving us a hyperbola instead of a unit circle. However, if we use this known result that hyperbolic cosine turns into this is really not so bad now. We can rewrite this as 1/2 e to the x plus e power -x. That means it's 1/2. We do a table lookup on e to the x. It's a summation x power of n divided by n factorial. But for emphasis and just for safety, here it is on that table. This is on our actual notes. This just prevents us from scrolling up and down. We're going to put this function in everywhere e to the x occurs. So for this e to the x, summation from 0 to infinity, x power of n divided by n factorial, plus. From this e to the x, a little bit trickier. We're throwing this -x in place of this x power of n right here. So it becomes summation from 0 to infinity. We have -x to power of n divided by n factorial. That's kind of inconvenient in a real sense though, because now we have two power series. We want a power series, one power series to represent hyperbolic cosine. We're not trying to derive it from scratch using 11.10 part 1 methods. We want to do it through this stuff. So here's what the next steps are going to look like. I think I'm going to need more horizontal space, so let me throw it back over here. 1/2 summation from 0 to infinity, x power of n, divide by n factorial. On this one, I want to separate the alternating part and rewrite this as summation from 0 to infinity, -1 to the nth power, n factorial. Excuse me, that's not n factorial, rather x power of n, then divide by n factorial there. So now we can do the interesting step. We have two series, and the first one goes like this. Let's use a bracket to rewrite this. So we just want to expand this out. Start at 0 rather, and we get a 1. When x is 1, we get an x. Let's just throw down a few of these terms. There'll be x squared over 2, x cubed over 3 factorial, x4 over 4 factorial. I think that should be enough. 5 terms. There's infinitely many more, so always a good idea to put that there to remind you it's an infinite sum. Let's do it again for this side, plus. We're putting 0 in for n, we still get a 1. When we plug in 1 for n though, the alternating starts to work for us, so we get minus x. Plug in 2 and we're back to x squared over 2 factorial, or just 2 if you prefer. And that's how this next term goes. Nice x cubed over 3 factorial plus x4 over 4 factorial, and so on in that pattern. And now if we really look hard at this sum, both of them taken together, notice that there's infinitely many cancellations next. X cancels with negative x, for example. What else? X cubed cancels with this x cubed, both divided by 3 factorial. Let's just convey that the next terms would cancel had we written them down. So all we're left with is a 1, x squared over 2 factorial, x4 over 4 factorial, but it's 2 copies because it survives in the second term, but it's being divided by 2, so we really only have to write it once. This becomes 1 plus x squared over 2 plus x4 over 4 factorial. We keep on that pattern, it goes x6 over 6 factorial, and so on. As a power series, it's a summation from 0 to infinity of no alternating on this one, and it's by evens. So this is x power 2n factorial. This is the power series representation for hyperbolic cosine at a radius of infinity. Now, comparing what we did with sine and cosine, that's messy. It's really easy to lose your way with this kind of stuff. You need complex numbers at the same exact time. It's just a giant mess when you really look at that. But the hyperbolics are nice. Well, nicer, let's say it that way. Not as much work to get to that kind of result. Also take a look at just how close this is to cosine itself. You get hyperbolic cosine by deleting the alternating part and coming down to that. Same idea with hyperbolic sine. Oh, it's not on this list at all. But if we go to sine and we want hyperbolic sine, we just delete the alternating part and you're in business. Well, let's try that out for hyperbolic sine. We do have a little bit of additional time. But any questions at all, folks, with where we're at with hyperbolic cosine's conclusion? Okay, let's try this out one last time. So this one is hyperbolic sine n x. By definition, it's 1/2 times e to the x minus e to the power of negative x. Like we mentioned with another problem, we don't really want to reinvent the wheel. It's practically the same thing, right? The only difference is the term in the middle. So that means if we go to write out the expansion, the only difference is that that is a negative sign instead of an addition sign. So let's scooch down to that exact step. Since every other step is completely identical, this becomes 1/2. Let's go with a bracket. All of these terms go in, 1 plus x squared over 2, x cubed over 3 factorial, plus x4 over 4 factorial, and so on, going forever in that direction. Here's our one change. I'll highlight that in yellow to show it. You have a minus here. Then 1 minus x. This one is alternating because of the negative x right here. So minus x plus x squared over 2 minus x cubed over 3 factorial plus x power 4 over 4 factorial minus and so on. So that's what it would look like if we expand out e to the x, e to the negative x, and put a minus sign this time in the middle. Now we have interesting cancellations again. For example, if you distribute this negative through, you get a -1. Canceling with the +1, this negative x becomes positive x, so you've got 2 of them, but then you're dividing it in half. You only keep the 1. Negative x squared over 2 becomes negative, cancels with the +1. Negative x squared over, positive x power 4 over 4 factorial becomes negative upon distribution, so that term gets canceled. So all that survives is these things. And there's not even 2 of them because of the 1/2 factor in front. Although this looks negative, remember it gets distributed through by the negative sign. That's really a positive x with this x. So just x survives. That's plus x cubed over 3 factorial plus, pattern continues with odds, x power 5 over 5 factorial plus x power 7 over 7 factorial, and so on in that order. If we rewrite this whole thing as one power series, it's a sum from 0 to infinity of x power 2n plus 1 divided by 2n plus 1 factorial, and the radius goes off to infinity on this one as well. So taking a look at our big table once again, sine x has this alternating part, but if you go to hyperbolic sine, it just becomes this altogether, remarkably similar with one major change, no alternating any longer on that one. So those are some of the interesting things you can do with power series. I think of these last two applications, the e to the ix, hyperbolic, cosine, hyperbolic, sine, as just purely more mathematical kinds of applications. And another way to think more about these kinds of functions. These are not very nice functions in a real sense. And the more and more you look at sine and cosine, even beyond this, the weirder they get. But any last questions, folks, with the conclusions here? Okay, again, these are some interesting problems. It goes a little bit beyond the material that we covered in the actual textbook itself. But if you come back to the final exam and you notice any one of these questions showing that this is true, coming up with a power series for Cauchy or a power series for Sinh using these methods, those would be decent extra credit questions at the very end of the final exam, just to make this kind of work a little bit more worthwhile. Well, I think this is a good stopping point because I did not prepare my material in time for chapter 10, but when we come back on Wednesday, we'll be in section 10.1. Chapter 10 is a pretty light chapter. That's why we saved it for the end of the semester, essentially. We don't want to do this right before finals week, for example. So chapter 10, we won't spend a whole lot of time on, and we're on great track for when we come back after Thanksgiving break. Looks like most of Wednesday, if not all, and Thursday we'll be reviewing for the final exam, the 4th and 5th of December. Well, have a great night, folks. We'll come back on Wednesday, finishing off chapter 10.